Hello everyone. Let's continue our discussion with the spice simulations. So till the last video we looked into a lot of theory about the voltage transfer characteristics of the CMOS. In this particular video and following videos we'll be doing some spice simulation and deriving those characteristics on real-time MOSFETs. Okay, we have some 350 or 250 nanometers MOSFETs already available with us. We'll try to do some spice simulations on those MOSFETs and see how does it look like and what happens when we fine tune some of the parameters that you see in the equations, in the voltage and the current equations. So we'll do with that. Before entering into the spice simulations, the first part is to create this spice deck. Okay, so we have to create this spice deck. Spice deck was nothing but a connectivity information about the netlist. So it's basically a netlist that has everything. It has got the connectivity information, it has got the inputs that has to be provided to the simulation, it has got tap points at which will take the output and so on. So it has got everything. So the first step is to create this spice deck. Okay, in the past videos we had created spice decks for a single NMOS, for NMOS only. In this case we have to create a spice deck for the complete netlist, and in this case the netlist looks a bit different than what we did before. So in this case you have the PMOS over here. The symbol of the PMOS is a bit different. Initially we saw the symbol of the PMOS with a circle over here. In this case the symbol of the PMOS looks something like this, where you see an arrow which is pointing towards outside, and in case of an NMOS the arrow is pointing towards inside. There are significances of these arrows. I'll come to that in a bit from now. So this is how your PMOS looks like. This is the substrate terminal and this is the substrate terminal of your NMOS, and this is the PMOS and this is the NMOS symbol. And the reason we are doing this, because in your spice deck or in your spice netlist we need to define the connectivity of your substrate as well. Substrate is a potential component or a potential pin on your NMOS and the PMOS or the transistors. So you need to define the connectivity of that substrate pin as well. Okay, and we also looked into the significance of the substrate pin, where it tunes the threshold voltage of your PMOS and NMOS. So we have already looked into all those. Okay, so this is your PMOS, this is your NMOS. There is a connectivity information. The source of your PMOS is connected to VDD, the source of your NMOS is connected to VSS, and you have your input voltage and you have your output load capacitor. So there is a lot of theory behind this output load capacitor. The value of the output load capacitor doesn't comes just like that. There are a lot of equations, there are a lot of theory that goes behind the computation of this particular load capacitor. But in this case we'll assume a load capacitor value, let's say 10 femtofarads, and move on. And in the next or in the advanced courses we'll be looking into how do we exactly get this load capacitor. Okay, so it is basically decided by the circuit that is connected, by the input capacitances of the circuit which is connected at this point. So we'll get into all those in the more advanced videos, in the videos where we're looking into the dynamic characteristics of your CMOS. In this case we are looking into the static behavior of your CMOS. So in this case we'll just assume a load value and move on. Okay, so we have to define the component values. The next thing is to define the component values. By the component values I mean the values for your PMOS and the NMOS. So in this case the PMOS is given the value of W by L as 0.375 by 0.25. It says your channel length is 250 nanometers or 0.25 micron, and your channel width is 0.375 micron or 375 nanometers. And same we are going for M2. So there is a scenario where we understand the PMOS should be wider than the NMOS, and we'll come to that, the reasons why the PMOS should be wider than NMOS. In this case we'll just assume the values of 0.375 and 0.375 both for PMOS and NMOS. So we are taking a same size PMOS and NMOS and see what happens in the characteristics. Ideally your PMOS should be twice or thrice bigger than your NMOS. By that I mean 0.375, it should be this should be 0.375 multiplied by 2, in that range. But there are again reasons and there are applications for both of them. You need this one, you need this kind of inverter, as well as an inverter which has got a PMOS bigger in size. You need both kind of inverters for your application. So we'll come into we'll get into those as in a bit from now. For now we'll just look into the PMOS and the NMOS of the same size. Okay, and see what happens to the characteristics. and the next component value that we have to decide is the output load. Basically we just assumed a value of 10 femtofarads over here. Basically this value comes from a lot of calculations. Basically the circuit that is connected at this node, the following circuit which is connected at this node, has got some input capacitances and all those things. So we have to look into and we have to compute those load capacitance. In this case we'll assume a value of 10 femtofarads. Okay, next we'll define the values of the input gate, the input gate voltage. So we'll assume a value of 2.5 volts. So generally if you have a node value of, if you have a channel length of 250 nanometers, usually the voltage is kept in the multiple of 250 nanometers. So in this case it's 2.5 volts. Had the channel length be zero point 0.1 micron, this would have been 1 volts, or and so on. So it's just a calculation that happens, and I'll get into the calculations in some time from now. For now we'll assume a gate voltage of 2.5 volts. Okay, we'll assume a drain voltage or the main supply voltage as 2.5 volts, and we'll move on. So these are the component values that we are picking up. Okay, we have these values for PMOS, we have the values for NMOS, the load capacitor, and the input and the output voltage, input and the supply voltage. Okay, and these are all the VSS terminals. So let's club the VSS together. So we have this common VSS for all the supplies that is present over here. Okay, next step is to identify the nodes. So for example, in the past couple of spice videos we have looked into what does a node mean. So in this case, node means there are those 2 points between which there is a component. For example, over here this and this becomes a node because in between there is one component. So in order to define this component in a spice netlist, you need a node. You need to say that this component lies between this and this node. So that's basically a definition of the node. For example, let's look into this and this node. This and this node. So in this case, this M1 transistor is defined between three nodes: this node, this one, and this one. Okay, so there are basically no components connected between this node and the transistor, this transistor and this node, this transistor and this node. So there are no components defined in between them. So we can very easily define this particular transistor in between these three nodes. Okay, let's pick up another component. For example, let's say we have this load capacitor. The load capacitor can be very well defined between this node and this node, because this is a node which is common to all of them, common to the VSS common node, and you have this particular node which is present at one of the parallel plate capacitor of your output load capacitor. Okay, so there is nothing other that is coming in. So had there been a resistor over here, then there would have been this node, and there will be another node which is present over here. Since there is nothing present between this point and this point, this can be considered as a potential node. So these nodes are basically required to define your spice netlist, and I'll show you in some time from now how basically these nodes are important. Similarly, if you look into this VDD can be very well defined between this node and this node. Okay, so let's name these nodes. We'll give this node name. We'll call this as in, we'll call this node as VDD, we'll call this node as out, and this node as 0. Since it's VSS, we'll call it as 0. So basically, if you want to define an output load capacitor, we'll say that the load capacitor lies between out and 0. If you want to define the VDD, we'll say that the VDD lies between VDD and 0. Okay, and we'll look into one of the definitions of this, but one of the applications of this particular nodes. So let's start writing this spice deck. Okay, so for example, these are just comments. Anything that starts with star are comments. So this is model description, and we'll start with the netlist description. So let's say M1, the MOSFET M1. You have the in the past video we have looked into the syntax of the MOSFET in a spice. It's drain, gate, source, a drain, gate, substrate, source. So M1 will be drain, so drain is out. If you see at this particular point, your drain is out. For the M1 MOSFET, your drain is connected to the out node, your gate is connected to the in node. Okay, your substrate is connected to the VDD node, and your source is also connected to the VDD node. Okay, so this particular till this point, this defines the connectivity of M1. PMOS says that this M1 is of type PMOS. Okay, W is 0.375 and L is 0.25. So this line completely describes this PMOS transistor, which is defined by the name M1. So M1 is connected between out, in, VDD and VDD. Okay, it's a type PMOS transistor. It has got a width of 0.375 micron. It has got an L of 0.25 micron. Okay, so what we'll do is since I'm running a bit late out of time, we'll stop at this moment, and in the next video we'll continue writing the spice deck and completing the spice deck and running a spice simulation on this deck. Okay, so let's try to do all this in the next video. Thank you.